All right, so I'll just start by advertising. So I'm sure all of you know about the Combustion Symposium. So that's happening this year in San Francisco in August. And that has a very big section about combustion chemistry kinetics. And maybe some of you are actually going to get papers there. The other big kinetics conference of great interest to combustion people is this one, the International Conference of Chemical Kinetics. And that's going to be next year in Ghent, Belgium. It's a very beautiful city. And then we'll go to Bruges. And so Ghent and Bruges were both in the movie Monuments Men. They were some of the action in Belgium was happening there. And so it looks just like it does. I think they actually filmed it on location. So if you want to go see what it's like, it's very nice. Kraft, who was featured in some of the slides I just showed you about the soot, he'll be giving one of the plenary lectures. Trular is very famous for calculating rate coefficients, so he'll give the other one. And then Seekins is a famous experimentalist for measuring rate coefficients. So you can hear some really nice talks there. And you can apply to give your own talks too. All right, let's see if I can figure out how to get back to the other one. I confused it again. All right, so if you want to understand about soot chemistry, you have to understand this mechanism. So this was the first mechanism that was at all close to reality for understanding how soot is formed. So this is acetylene, and the model is based on the idea that if you have some radicals and they add acetylene, you can form phenyl radical, and then you can keep on adding these C2 units onto the C6 core and keep growing and make more and more polycyclic aromatics and so on. And the same sequence of steps happens. You have a hydrogen abstraction, and then you have an acetylene addition. And I don't know how that makes HACA. Hydrogen abstraction, carbon addition. Okay, but the carbon is always added in the form of acetylene. And that's realistic for a lot of these systems. You mostly make ethylene in the fuel pyrolysis. So if you let it cook too long, you make bushels of acetylene. And so acetylene is it's very reactive, so it's easy to add to it. And also, the radical you make after you add is still very reactive. So this can keep going as a polymerization reaction. So the dominant species is acetylene. And they model this, and they started out doing it all Arrhenius kinetics. I think they also did with pressure dependence. It's been studied pretty well, and a lot of the steps are known really well. And actually, Hai Wang, I think he did this when he was a graduate student or a postdoc or something like that, and Frank Luck's lab. Now, this is a frightening thing. This is a sensitivity analysis for the formation of pyrene, which is one of these big polycyclic aromatics, which people use as like to stand in for soot. So they make a kinetic model. They can't make the kinetic model go all the way to soot. So they say, well, if it gets up to pyrene, it's probably going to go to soot. And so this is how the yield of pyrene depends on all these rate coefficients. So like all the reactions, all the cases I've shown you so far, it always depends on H plus O2. But the sensitivity is not that big to H plus O2. But it depends on all kinds of other reactions. There's lots of them here, and all kinds of things. And so this is scary, because we really like the kinetic models like this. This is more typical, where you have like two reactions that stick out that you're really sensitive to, and you don't have to worry about them anymore, and they're all gone. So that makes it a lot simpler. You can really just focus on a couple of rate controlling steps and make sure you really have those numbers really well, and then you're tremendously better. But in this case, where you have a lot of reactions that you're sensitive to, it makes it confusing. So you have regular flame chemistry reactions you're sensitive to, and reactions that make the first aromatic ring you're sensitive to. These are the most sensitive. But then you have still very significant sensitivities to these really big ones. This is like an A3, that's a 3-ring polycyclic aromatic, for example. It's like, why? Why should I be sensitive to such a big thing? And part of this is just the rate coefficients. If you do the sensitivities to the thermochemistry, you find you're also sensitive to a lot of thermochemistry that has to be done accurately too. So this is part of the reason why this is not solved, is that at least as best we understand it now, we're sensitive to many, many numbers, and only maybe half of them we really know. And so people are gradually working on the rest. But I'm afraid that if they do that, and then they extend the model, they'll find out they're sensitive to a whole bunch of other reactions that they haven't dealt with yet. And it's really that the whole, from the very beginning, you saw the potential energy surface. A lot of species have approximately the same free energies. So you get a lot of species in pretty significant concentrations. And that makes it confusing to model. Whereas in a lot of cases there's like a dominant species. You mostly have, X and Y. And you don't have to worry that much about Z because the concentration of Z is a lot different. But here you have a lot of these aromatic species have comparable concentrations because their free energies are all about the same. So you have to worry about making sure that the rate coefficients for all of them are at least semi-reasonable. Otherwise, you really screw up the model. And they all interconvert via the Hecke, for example. So anyway, that's a problem. So there's what we learned from this, is that the pH formation is sensitive to a multitude of elementary steps. And it's going to require precision that, at least at the time when he gave this talk in 2010, it looked to him like this was not going to be available. I think that things have improved a lot, but maybe he's still right. I'm not sure. And it also can be sensitive to the fuel structures, because it's basically just a sensitive thing. And also, it's possible that there's other pathways to make the pHs. And in fact, this is prescient. So he gave this talk in 2010. Since that time, maybe 3 or 4 additional pathways to make the soot molecules have been found. So it's one of these systems where it looks like the nature wants to make soot, and it doesn't just rely on one way to make soot. It's another way. Sort of like the Nile Delta. The water from Uganda wants to get to the Mediterranean, and if you block up one direction, it doesn't matter. It's going to find some other way to get there. There's lots of little rivulets, and they all can go. And this is an example of the thermochemistry. So you can see that this whole scale is only 1.5 kcals per mole per carbon atom here. And the things are bouncing around in that range, lots and lots of different species. And these are not all the species. There's a lot of other isomers in there. So you have to worry about a lot of species. It makes it kind of confusing. Now, this is a really important. Back in 1990, Farr and Stein hypothesized that the propargyl, the C3 plus C3, might be really important, but nobody knew how to probe it at that time. But then, since then, starting about 2003, there's some really great calculations that, and then a lot of good experiments too, that verify that there's this very complicated thing. The C3, it's 2 linear C3s. These molecules here, they get together, but they get together and then they can cyclize. And eventually they make a 5-membered ring, and then eventually a 6-membered ring. And that comes out as phenyl radicals plus H atoms. And that the outlet here is downhill from the inlet. So this is one of these well skipping reactions. You skip over all these wells and end up over here. It has a very funky temperature and pressure dependence that we looked at a little bit when we did the eigenvalue stuff. And then other people, these are recent papers that discovered different pathways that make aromatic rings in these conditions. And there's a really nice advances in synchrotron techniques for measuring all the species you make, so you can verify the models. And so this is from Fei Qi's lab in China, and Nils Hansen at Lawrence Berkeley Lab has also very recently built an apparatus to do this, and so you can measure all the different isomers that you're making, and he sees like thousands and thousands of species, and he can quantitate them all. And so you really have a way to validate the really complicated models. But this is a challenging one for both the modelers because it's so complicated, and then the experimentalists trying to validate if the data really proves the model or not. Similar to the one I showed you for the flat flame, where we saw a lot of species. We thought we were great, but then actually 3 different models gave basically the same results. A similar thing can happen here, so you have to be really careful to interpret it correctly. All right. And one thing that, oh, here we go. So there's different hypotheses about how the soot gets nucleated. So the one way to look at this is similar to, you know, if you have sugar and you put more sugar in water, eventually the sugar will crystallize out and you can make rock candy. Do you have any idea of this? Or, you know, where people try to make proteins to do crystallography to measure the protein. They put a lot of protein in water and they kind of evaporate some of the water and then they hope that it'll make a beautiful crystal of the protein and then they can put that in an X-ray machine and measure the crystal structure. So in all these cases, there's two steps. There's a nucleation and a growth of the crystals. So we have the same kind of thing. We have to nucleate a soot particle in the gas phase and then we have to have it grow. And we have to understand both of those steps. And they're both a little bit complicated. And this nucleation has been particularly confusing. And I say nucleation in general is very confusing because what you measure at the end is always the grown crystals or the grown soot. And then you're trying to back up and figure out what happened the very instant it started, when it nucleated. And it's hard to experimentally see it. So then you have to make hypotheses about what happened, and then the theories have some trouble with it. Anyway, at the time that Hai gave this talk, there were 3 competing theories about what the nuclei looked like. Hohmann, some time ago, had proposed that you make a polycyclic aromatic thing that looks sort of like C60, like the fullerene, except it kind of makes a spiral, and that could keep growing. And the thermo works out well for this one, but the kinetics are kind of weird of how do you make this thing grow that way, because there's a lot of other ways it could grow. Franklock and Wang and Miller all went with theories that maybe you make some flat graphene type thing, and the graphene layers just line up like graphite. So that was their theory. And then Violi and Diana, who's a very famous combustion scientist in Italy, they proposed that maybe you make some little pyrene rings and then they have linkages to other aromatic rings and you sort of have a tied together pyrene rings. I should comment that this structure is what you get in heavy oils. If you look at like asphalt, it actually looks like this. You have some polycyclic aromatic core and then you have some linkage and some other one. Same in coal, it looks like this. So it's kind of believable that you might make that. And so if you compare the kinetic models, the experiments now are very conclusively say that what you have is a non-monotonic dependence of the number of particles versus the size. You have like small ones, and then you have like a dip, and then you have bigger ones. Whereas if you did a first order nucleation kinetics model, you'd always get particle size distributions that just have a single hump. So this indicates that the thing has to be nonlinear. Otherwise, the fact that you see the distributions like this, and you get these persistent bimodality. It's called a bimodal distribution. And so you see it when you first start. It looks unimodal, but very quickly you build in this bimodality. If you sample different parts of the flame, as you go higher and up in the flame, it seems more and more bimodal, like that. And also in the mass spectrum, this is kind of cool, is you see humps. So you see a whole lot of light stuff in the mass spectrum of a sooting flame, and then you see a hump of heavier stuff, and then you see another hump of heavier stuff, and the delta between these guys is approximately 500 AMU, which corresponds to about 40 carbon atoms. So it suggests you have some kind of chunk that's approximately 40 carbon atom size that you have one of those chunks, and then 2 of the chunks come together, and then maybe 3 of the chunks come together over here and make the little hump over there. So that leads you to suggest hypotheses of things that can make 20 carbon or 40 carbon sized chunks. And so there's a bunch of proposals about that, about what could be the kinetics and what species you could be making it would be stable that would be that size and might live, in order to glom one to another one. All right, so the fact you see the chunks rules out the Hohmann hypothesis. It can't be right. So this is not the nucleus. So these guys are still viable. Then you can look at the temperature dependence of the particle size distributions and do analyses, and it also rules out that third mechanism. And then you can try to figure out what size chunk you would need for things to glom together the way that mechanism 2 works. So in this mechanism, these guys are not chemically bonded to each other. They're just sitting next to each other. And they're sort of attracted by van der Waals interactions. So then you have to wonder how big would they have to be that the van der Waals interactions would be strong enough. So this is back to our sealing temperature issue. Right? There's a sealing temperature. If you want two things to come stick together, you need the delta H to beat the T delta S. Right? So by looking at the temperature dependence, you can figure out if this is reasonable or not. And the binding energy, if you get up to coronine sized, which is coronine's like C25, I think, something like that, it's still not strong enough to explain it. See, coronine is non-binding. The delta G, the entropy is just too much. So the T delta S term is too big. It really wants to separate. There's such a high temperature, it wants to evaporate, it doesn't want to stick together. If you go to even circumcoronine, which is maybe 30 carbons, is still not enough. But this kind of supports the idea of the 40 carbon chunks. Do you see back here? If you had a 40 carbon chunk, maybe the thermo would be enough to make them just bond together. So maybe this hypothesis is still correct, but these chunks have to be 40 carbon sized. But nobody knows. No one's seen it yet, as far as I know. But a lot of the small molecules. So High thought it was unreasonable. They have to go up to 40, so he said, forget it. And he crossed out his own hypothesis and said, okay, well, maybe the Diana hypothesis is right. But it all makes you wonder, why does the thing stick together? Why do I want to make, I have all these gases, I'm at super high temperature. Why do they want to stick together at all? Because if you compute the T delta S, it's really huge. So you need to have quite a strong delta H, but what can possibly be strong enough to make them stick together? And it has to be a lot of them that want to stick together because all of a sudden, all my mass goes from being acetylene to being all this black stuff. So something really fast has to happen. So one theory is that maybe you're making radicals. So when you make these long extended structures with a lot of double bonds and triple bonds in them, then it turns out that you can have what are called persistent radicals. Radicals, even at room temperature, they're stable. Really the molecules, they don't care about whether the electrons are paired up or not. They can have them unpaired, it doesn't matter, because the electrons are like flopping around on these extended resonance systems. So this is benzene, only has 3, but suppose you had 100 double bonds, all sequential, then you could actually almost have like a free electron gas, the electrons just wandering around among the system. And in that case, the pairing energy is not so strong. So you could have unpaired electrons, and maybe unpaired electrons, they're known to react very fast, so maybe that could explain it. And there's a bunch of papers, people have theory about this. There's also some experiments that show that you do have radicals existing. Many papers you see recently all about whether or not you have radicals in these systems. So if it's true that you have some big giant radical, and then the radical is making things stick together by adding, we really have to understand what's the thermo, what are the rates, we have to detect them, make sure they're really there, and figure out their mechanism. So this is like a proposal by Hai Wang about what the community should do to try to track this down. As far as I know, people work on this a little bit, but it's not really been addressed, or it's not resolved issue. And you notice if you try to explain the growth after you nucleate, if you use the Haka mechanism, you get a steady state formula like this, which depends on the concentration of the H atoms, because you need an H abstraction at each step. And so that implies that you need to have a high enough temperature, a high enough amount of H atoms to keep the growth going, otherwise it'll stop. And here's the experiments where they measured at different distances from the burner face what the size particle distributions were. And they actually looked at those subparticles by electron microscopy. And they showed that, they call it baby soot, the soot you get early, is completely different than the mature soot. So the mature soot looks like graphite, kind of. But the baby soot looks like liquid. It's not solid, actually. It's like drops. It's not rigid. And it has a C to H ratio 1:1, whereas mature soot has about 8:1. So it has a lot more hydrogen atoms in it. And And it has a lot of aliphatic regions, which are like carbons that are not in double bonds, like CH2 groups. So what the heck? This is really confusing because we're above the ceiling temperature, so you wouldn't think that things with CH2 groups in them could live. So this is very mysterious. But there's electron microreactors. You can see it looks like eggs. You fry an egg, you have like a yolk, some like solid part, and then around it's like a halo of the white. So there's some egg white oozing out of the soot particles onto the thing. You see them here, like some chunk of soot with some liquidy stuff around it. And in fact, in engine experiments, when people look at soot, they often see this. They call it the oil-soluble fraction. If you take some soot in a filter and then you extract it, you put it like a solvent, you can dissolve a lot of liquid hydrocarbon. It's almost half the mass of the soot is actually not solid. It's like liquid stuff that you can dissolve. So that's kind of weird. I think nobody knows what that is either. And if you do FTIR, you can see that these areas that are liquid are aliphatic. That means like alkanes. But that's totally strange, right? Because in the flame, he's detecting after the flame. He put stuff through a burner. It got hot. Then after the flame, he was making soot because it was fuel rich in his case. All the alkanes should have been burned up, right? Basically, by my theory, I told you they'd all go to alkenes, right? I should just have like propene and ethylene. I shouldn't have any alkane left. So how come he's seeing alkane stuck on his soot at the end? So this is really weird. And so his theory about this is maybe you are making a large alkene, and maybe you have some persistent radical in the solid soot particle, and maybe that radical is sticking onto the double bond in the large alkene, and that's pinning the alkene to the soot surface. So maybe that's true. So this is the kind of thing we're trying to figure out right now. And so people like Hai Wang have been doing a lot of like different analytical methods to try to figure out what the material really is. People did electron spin resonance, where you stick the thing in a special machine that measures radicals. And if you stick a piece of coal in it, you actually see free radicals are sitting there, even though it's been sitting in the earth for a gazillion years. The radical has not gone away. So somehow the radicals are stuck and they don't react, or they're stable or something. Wang did a study, a theoretical model that predicted you'd have to have the radicals still there in order to explain the soot observations. If you measure the soot from pyrolysis of jet fuel, for example, Seraphim saw that you saw this many spins per gram, which is a lot. 1 of every 50 carbon atoms has a radical site on it. It's kind of weird too. And then another strange thing is that soot, water will stick to soot. So why that is strange. So he thinks that maybe that says it's radicals. Maybe the water is sticking to the radical sites instead. I don't know. That seems highly speculative to me. But anyway, there's a lot of like mysterious clues that no one's put together into the story. We need Sherlock Holmes to figure out what happened to soot. So anyway, the soot is formed. Initially, it has a lot of liquidy aliphatic stuff in it. In some experiments, that stuff stays as measured as a soluble organic fraction. In some experiments, the soot gets cooked some more, and all that stuff turns into aromatics too. And so you end up with a solid soot. There's some possibilities that you have radicals. These big giant soot moieties could actually sustain radicals that live. And in fact, you know it, because in coal, you have very similar moieties, and they actually have radicals in them. And the radicals are measured in the soot, right? They measured, these guys measured it from soot. There's a bunch of radicals in there. So there are radicals. What they're doing, we don't know, but they're there. So then Wang did calculations about different moieties to try and figure out what the thermochemistry would be of those radicals. And now he thinks that maybe this is what's going on, is that originally you have the small molecules, you make some aromatics, they grow polycyclic aromatics, they start to glom together, and somehow this is where magic occurs. These things suddenly bind together and really become stable and start going to all the little alkyl chains on the outsides. I don't know if this is the correct picture at all, but that's the Wang picture as of 2010. I said the importance of having good cartoons. So this is you're trying to get the cartoon that really corresponds to the physical phenomena. So he says that we've always thought it's really hard to make soot. In our kinetic models, we can never make soot. Every time we try to do it, the equilibrium says it shouldn't be formed. But if you look in the experiment, you see it all the time, lots and lots of soot. So he says that maybe we're doing it all wrong. Maybe soot is really where it wants to go, and we're upside down. It's actually that it's odd that we don't see the soot being formed right away, and that's a better way to look at it. And then he finally, just to end his talk, he pointed out that this was all about soot, but there's a lot of other methods called combustion synthesis. Maybe some of you do this, where you try to use flames to make powders on purpose. And titania, which is the ingredient in paint, it makes it opaque, is manufactured in flames. Fumed silica is also, and that's what's used to make fiber optics, is also manufactured in flames. So you can turn this tendency that the flames want to make particles to your benefit if you make it the particles you want to make. And there's a big business doing that. And that's all I had from Hi. Other questions about that? Yeah.
If a fuel itself has aromatic content, how the aromatic content will contribute to soot formation?
Yes. Yeah. So, I meant to show some slides, but I don't have them right here. But if you start with a fuel like benzene or acetylene, you'll make more soot than other fuels. There's a lot of weird things about this. So, for example, if you feed benzene into a diesel engine, and then you measure the soot at the end, and you isotopically label the original benzene, from studies of the statistics of how often two labeled atoms get next to each other, you can figure out that almost all the benzene must have been ripped apart. So it did not stay as benzene. It burned part of the way, and then it reassembled back into benzene and shows up as pairs of isotope atoms. And it rips down to C2 moieties. So maybe almost all the fuel goes down to acetylene, maybe. I don't know. That's the one possible interpretation of that. But you definitely do see more soot when you start with benzene. So maybe you already have some of the nuclei. Maybe some of the nuclei do survive. So the benzene molecules come through and they immediately make the soot. Also, you can get a methane flame that would not be sooting at all, but you can run it kind of rich, so it's close to sooting. And then if you put in a teeny tiny bit of parts per million of some other bigger molecule, you can induce benzene formation like crazy. And so CEFRC and McAnally have done a whole ton of experiments where they just have a nice methane flame, no soot, no benzene, and they just dribble in a few ppm of this guy, a few ppm of that guy, and they have a table of like 1,000 molecules, and they call the sooting propensity index or something. They have a number of like, if you put in so many ppm of this, how many ppm of benzene does he measure being formed in the flame, in a diffusion flame? And so there's, it's like just a little bit can tip the system over. Exactly how it works, nobody knows. So I did a model of one of his experiments, and we predicted the same number of benzene that he saw, basically. So if you do the detailed whole model, it comes out, but I feel like I don't have the conceptual understanding. So I have a detailed model, it's correct. I know all the steps, but it still seems like there's a more basic thing, like why does this work? Why does that experiment work? I don't know. But anyway, that's the state of the art. So it means there's plenty of opportunity for you guys if you want to contribute. The old guys haven't figured this out yet. So, any more about this? All right, so I was going to change topics now. I'll talk a tiny bit more about soot, and then I'm going to start talking about ignition. So soot and ignition are two cases where the computational fluid dynamics are really not dominating. So the soot is mostly forming over to the right here, or to the left here, of the flame front. And so it's forming where it's hot, but it's basically a homogeneous chemistry. Whatever you do with the mixing isn't mattering, because it's all fuel. It's not inhomogeneous at all. And so you can mix it to try to make it not so bad as you can try to force it up to the flame front to get the stuff to burn. But that's about all you can do. If you let it sit, it's gonna soot. And the rate that happens is really all controlled by the chemistry, and details about exactly what your fuel mixture is make a difference, but for reasons that we don't completely understand. And the same thing is with ignition. So if you don't have a flame yet, and you just want to see how something spontaneously ignites, that's all controlled by chemistry as well. And really the transport phenomena are really minor effects on it. So that's why I chose these two topics, actually. I mean, there's a lot of other combustion phenomena, but most of them are really heavily controlled by the I still have it. That's great. Do I still have it? Yes. All right. All right, so as I was saying, for soot, there are many unresolved mysteries. And so I hope you have all these ideas of more mysteries. There's a lot of experiments and a lot of calculations in soot. So if you want to get into this, you actually have to read a lot of literature. But I can assure you that nobody knows the answer. So after you read literature, maybe you can propose the new idea that's actually the correct explanation and understanding, which would be really great, because I sure would like somebody to explain it to me. We talked about the idea of a ceiling temperature. So I think there should be a ceiling temperature for soot. So the initial reaction, say from ethylene down to acetylene, this has a Kc that increases with temperature. So at higher temperatures, it should go more to the right, and that's because it has a release of the hydrogen and makes more entropy. But the later steps look like there are a bunch of small molecules coming together to make a single big molecule. And that one should have delta S that is negative, because you're losing degrees of freedom, losing particles. And so they look like they should have a ceiling temperature. That means that they have to occur at low temperature. If the temperature is too high, it shouldn't go in the right direction. It should go the other way around, right? And so this is weird that this reaction requires a temperature high enough to drive it to the right. This reaction, remember, requires a temperature low enough to drive it to the right. And so it sort of suggests that maybe there's some temperature band where soot can form. And I don't know the literature well enough. I think sometimes people see this, that when the temperature is too low, they don't see soot, and when the temperature is too high, they don't see soot. But other experiments I've seen, sometimes they see it at low temperature too. And then this has to go, is all soot the same? And maybe there's different reactions that are happening to make different kinds of soot. But anyway, but this would sort of suggest there should be a temperature band. And the real question is, are there other ways that these small molecules can get together and maybe somehow release a second molecule? So suppose if these guys could get together and kick out another H2 molecule, then that would change the whole entropy situation a lot. And then the whole thermochemistry would be different. And the ceiling temperature would change all over the place. And how big these things can get, I think, should depend very sensibly on the thermochemistry, which is unfortunately not known very accurately. So there's a whole line of research that people do trying to make better and better thermochemistry for the polycyclic aromatics. But the problem is that actually a problem with that is synthesis, that they can synthesize up to like 25 or 30 carbon atoms pretty well. But then trying to, if it's really you need a 40 carbon chunk, then it's a lot of them, and they're hard to synthesize and know what you made. So it makes it tough to do the experimental calorimetry. All right, so suppose we make the soot. I mean, we do make the soot. All right, we know this. A very interesting thing is that if you have something, say a diesel at a high load, and you take a video inside with an optical engine, look inside, you see just bushels of soot. The whole thing is opaque. It's lots and lots of soot. And a very high fraction of all the carbon in the fuel is being converted into soot. But then, at the end, coming out the tailpipe is not very much soot. And so this idea is that something like 99% of the soot is actually being burned out inside the diesel engine. So that's kind of cool. But then I say, well, why is it not 100%? Why do we have to worry about soot? If we can burn 99%, why can't we burn it all? And so here's hypotheses about this, and maybe some of you guys know better than me. One hypothesis, or a phenomenon that's for sure true, is that when you make a lot of soot, you get a lot of radiation. And so the local temperature where the soot is can drop quite a lot because you lose heat. You get rid of the energy from that region because you send it somewhere else. And so maybe the temperature drops so much that the reactions that consume the soot, that burn the soot out, die because it got too cold. That's one possibility. Maybe it's turbulent and there's some kind of local extinction event because the strain is so high. And just by luck, some soot particles leak through when there's sort of like perforations in the flame front. The flame front is steady, but the turbulent waves go through. Sometimes they make the flame hotter. Sometimes they make they have such a high strain rate that they kill the flame temporarily. Maybe just at that moment, one of the soot particles got through, and then it never gets burned up. So that's a possibility. Maybe the soot is really burning the whole time, but the kinetics are just too slow, and we run out of OHs. So maybe our flame is too weak or something, and so we don't get to burn out. Of course, I don't know why it's strong enough to burn out 99%, and it can't burn out the last percent. I don't know. Maybe some places in the cylinder, the flame is stronger than others. And I think maybe my conclusion is we just don't know a lot about soot burnout. This is a very important topic. If you could, right now in all the trucks, they're putting in these diesel particulate filters. Any of you guys work on these? And that imposes a fuel economy problem for all the trucks, because you have to now have an exhaust pressure high enough to push the exhaust through the filter. And so then you have to do some complicated thing to keep burning the soot off of the filter. The engineers are smart and they figure out how to do this. It works, but it's just like another whole piece of kit that you're adding. It's adding cost. It's subtracting a little bit of fuel economy. And it's making more maintenance. And it's just because we couldn't get rid of that 1% in the cylinder. So if we could figure out how to just get rid of the 1%, then we wouldn't have to do that whole thing. All right, that's enough about soot. Let's talk about premix flames for a minute. Premix flames, one thing you're really interested in is the flame speed. And the flame speed is a reaction diffusion thing. This is a very classic case. If you have a simple analysis, we would say the flame speed should scale as the square root of the reaction rate and the square root of the diffusivity. Because the way that the flame is propagating is you're making a big gradient of temperature and of radicals, and then those are diffusing into the fuel and air that hasn't been burned yet. And that's making the reaction. Maybe if I draw a picture, it might help. Okay, so that was the diffusion flame where the fuel was on one side and the air on the other side. So we have a premix flame. We have the fuel plus the oxygen over on this side. We have the exhaust over here. So this is the CO2 plus the steam. Here's the flame front. And again, we have a big gradient, say in the temperature, and a big gradient in the radicals. And because of the steep gradient here, there's diffusion that way of the radicals and of the heat, the heat into the unburned fuel and oxygen. And when the temperature gets hot enough and enough radicals get here, then this fuel and oxygen starts to burn. So it wasn't burned here yet, but now this zone here is going to start burning because the radicals and the heat coming from the flame are going to drive it. And the flame speed in this kind of case, the size of the diffusion rates depend on the steepness of the gradient. The gradient will be steeper if the reaction is faster, releasing the temperature more. It's sort of like the thinness here. So the more reactive the more reactive the fuel-air mixture is, the steeper the gradient, which will make the diffusion faster too. So the flame speed depends on the diffusivity and also on the reactivity. And simplest idea is it's sort of square root of each. There's a recent review by Ed Law's group on lots and lots of fuels. It's like a 100-page review. And basically, my conclusion from this is that most fuels have similar flame speeds. And why is that? Well, most fuels also have similar adiabatic flame temperatures at the conditions that we usually run them. And also similar thermal diffusivities. Mostly it's nitrogen, because we're burning the fuels in air. So the thermal diffusivity of nitrogen doesn't care what fuel it is. And so the heat flux is more or less the same, similar anyway. And then there's sort of some kind of compensation effect that when you have, if you had some fuel that was burning a little bit faster, then locally you have like a diffusional loss of the radicals and the temperature that increases. So it sort of partially compensates. So if you have a fuel that's more reactive, it doesn't really, this thing is sort of self-limiting. You can't really make it go infinitely fast to the left. And you can do detailed simulations of this, and there's computer programs like Premix that do it for you, and it works. They work fine, basically. Something that you should be aware of is that a lot of discussions in literature assume the Lewis number is 1 for premixed flames. That's pretty good for methane air flames, but for lots of other flames, there's some regimes where the Lewis number equals 1 approximation is completely wrong. And there's some recent papers about this by Law and by Agafopoulos, and this resolves some mysteries in the flame speed literature. There's a couple fuels that are really strange. So for example, hydrogen, of course, makes a lot more H atoms than anything other fuel, because every time you attack hydrogen, you always make another H atom. And the H2 also diffuses faster than most normal fuels. So it can even diffuse significantly forward into the flame. So normally we talk about the fuel and the oxygen are heavy compared to the H atoms. So the H atoms are diffusing this way. But in the case, if the fuel was not a hydrocarbon, but instead was just H2, the H2 diffusion this way is actually could be significant too. Because you'd have a reverse gradient, that the fuel is like this. Right. And acetylene is odd too. I think this has to do with the details of acetylene chemistry, which is kind of different than all the other hydrocarbons. All right, and then finally, I want to talk about ignition. And this is my baby I really like. So ignition chemistry is wild. It changes tremendously with temperature and also some with pressure. If the temperature is high enough, it's not confusing at all. So the temperature is really high. You make a lot of radicals by H plus O2 to OH plus O. And these guys attack the fuel, and that makes more H radicals, and it goes and goes and goes. Boom. And you get very short ignition delays at high temperatures. And the models that just model basically H plus O2, and then have these guys react in the fuels, and then how many H atoms do you get per fuel. Once you put the model in, those parameters are enough to basically get the numbers about right for the ignition delays in shock tube experiments. However, when you go lower temperatures, things change a lot. So if you get low enough temperature that this reaction is not really significant, because instead it goes H plus O2 plus M to HO2, and sort of wipes out this channel. At those temperatures, things are really confusing. And the first confusing thing is two-stage ignition. So if you look at a lot of fuels, this is their ignition delay versus the temperature. And a lot of fuels have an ignition delay like this, and then it doubles back. So the ignition delay gets, as you'd expect, gets shorter and shorter the hotter you get, until you get to a certain temperature around maybe 750 Kelvin. And then it goes back the other way, and it goes up to maybe 850 Kelvin. You reach a maximum in the ignition delay, and then it starts getting faster and faster, as you'd expect. And there's almost like there's two Arrhenius plots. There's like an Arrhenius plot down here at low temperature, and there's another one over here at high temperature. And then in between it's doing some funky connection thing. If you look in detail at what's happening, you can see that the temperature is rising at this point, and then it stops rising, and there's like a second induction period, and then it really rises. I'll show you a picture of that in a second. And you can measure this first temperature rise, the time it takes until you get the first temperature rise. And that's what these hollow circles are. So this is all experiment. So the red ones are for dimethyl ether. The green ones are for methyl cyclohexane. A lot of fuels look like this. At low temperatures, you can see that the two humps, but they're really close together. So if you look at the plot of temperature versus time, if you initially heat the fuel to some temperature, and then you wait, nothing's happening, and then you'll see a little dink, the temperature goes up a little bit, and then it decides that it can't quite go yet, and just nothing happens for a long time, and it goes kaboom. So that's the two-stage ignition. And when you go low enough low in temperature, what happens is this is longer, and you see the little dink, and then you see kaboom almost right away afterwards. So that's the right-hand side of that plot up there, is where the two times are very similar. So this first time is tau 1, and there's another time here is like tau overall, the big explosion, when the temperature really jumps up.
Does that, when you have the span between the two temperature increases, does that also tend to coincide with a reduction in the net amount of radicals in your radical pool to choose from?
In these experiments, usually all they can measure is like the pressure, which is proportional to the temperature. And what the radicals are doing, okay, who knows? And you know, when you look at it, with most experimental methods, it doesn't look like anything's happening. I mean, the temperature is like hardly changing. You can't detect it even. And then you start seeing a little tiny bit of something happens, and then it looks like nothing happened. And then you see really something happens. It makes a heck of a loud noise, and all of a sudden everything's CO2, and it's a big mess. Okay, so that's the situation. So now we go to calculations. So for propane, we actually got all the species we could imagine and all the rate constants you could imagine, and we calculated them all as best we could with really fancy quantum mechanics. So we think we have a good model for propane. And this is what is predicted to happen in propane. So the temperature is basically predicted to go nothing, 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 a little dink up, nothing, 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 boom. Okay, so that's looks like a regular fuel. And if you look at what the species are predicted, the OH is predicted to rise. This is a log plot for OH. It's basically rising exponentially from 10 to the minus 17 kind of at the beginning up to maybe 10 to the minus 12 moles per cc. So that's what, like 5 orders of magnitude increase in the OH concentration during this time when you can't see anything happening. So the temperature's not doing anything. The radicals started basically at 0. And all of a sudden, they're going up and going up, and they're growing up exponentially. They're growing really fast. But they started at such a low level that it takes a long time for them to get up there. And then something happens, and they keep on growing exponentially, but at a slower exponential rise. So this is like a double exponential rise. It's a fast one and then a slower one. And then they dip. The OHs go down, and that happens just around the same time that the temperature shows a little kink experimentally. And then the OH gets about flat, and then kaboom. And the OH gets really high, and the temperature gets high, and the whole thing burns up. Okay, any questions? This should be perfectly obvious, right? All right, so that's the solution of the ODE, says that that's what happens. So when I looked at that, I said, well, I don't know what's going on, but I do know that I could call this part A and this part B. So before everybody called this stage 1, because they just saw, this is all was seen experimentally is it's flat. So they called it, they assumed it was the same thing going on the whole time. But it looks to me like 2 different things are happening here, this and then this. So I think I call it A and B. Stage 1A, stage 1B. Okay, and then this second part's called stage 2. I don't know what's going on there. I don't want to talk about that today. So then I looked at the other species in the simulation. So the fuel is being consumed a little bit. Around the time when the kink happens in the temperature, you can see some substantial fuel consumption, but there's still a lot of fuel. Like 90% of the fuel is left. And then during the second stage, the temperature is going up some more and the fuel is being consumed. And when you get to the real explosion, all the fuel is consumed and the whole thing explodes. This species, the keto hydroperoxide, this is a very important one. So this one is exponentially rising until about this time, and then it keels over and becomes a maximum, and then it actually goes away. And it all goes away just about the same time that the temperature rise happens for tau 1. So maybe this is somehow related to the A and B thing. I don't know. And then around the time that this is hitting its maximum, you start making pretty much formaldehyde. It hits a maximum and goes away at the kink. And the hydrogen peroxide starts to come in. It does a little kink around the same time as the temperature kink, and then it grows up and it makes the explosion. Okay. Tau lambda is the end of stage 1A. Stage 1A. So tau lambda right here. So this is the end of when it's a perfect single exponential. The OH is a perfect single exponential. In fact, the keto, this guy is a perfect single exponential too, up until this time. And at this time is when the OH starts to rise at a different exponential rate, a different rise constant. And here it's, I think the same thing happens to this guy. It stops rising quite as fast, and then it actually keels over, goes through a point of inflection. So that's kind of interesting. Now you see the problem for the experimentalists is these are the full-scale values. So you can see the full-scale value of the keto hydroperoxide, which is the important species here that's doing this funky thing, is only 25 ppm. So up here would be 25 ppm, I think. So this is only like I don't know, what's that? 10 ppm. So you need a pretty good detection method if you're going to see the 10 ppm. And you got to look quick before the whole thing burns up, because a big fire is about to happen. Now these are the reactions, and you basically have your fuel, it gets attacked by OH, it makes a fuel radical, it adds O2, it makes a peroxyl radical. The radical could, instead of adding O2, it could beta fission and make the alkene. So that's what we talked about before for diffusion flames. But at low temperatures, this rate is endothermic. This is endothermic, so it gets slower at lower temperatures. And if you have enough oxygen, this is pretty important. So you actually make a lot of RO2. But this well is not that deep, so this is equilibrated reaction depending exactly on your temperature. At low enough temperature, it mostly goes this way. This guy has several choices, but the thing it does the most in most gas-phase systems is it isomerizes to this other species. But this is reversible also. This species can react with oxygen quickly. If it does, then you get down to here, and then this species does an intermolecular isomerization to this guy. This guy loses an OH radical, gives off an OH radical, and makes the keto hydroperoxide, which is the one I showed. So this main sequence is the main chain branching pathway. It makes a lot of radicals, because this peroxide later is going to break and make 2 radicals. And this one accumulates because this last step is very slow. It's very endothermic. There's a lot of side channels. Some of these red ones get rid of OHs. Some of the green ones make OHs. There's a complicated competition between all these things. If you change the fuel structure, you'll change the relative ratios of some of these competitions. And so the fuel structure really affects the ignition delay a lot. And this is really well known. So I showed you before for the butanols, you change the position of one methyl group, and you change the octane number by 14 units. And they're similar with a lot of other. It's known for many fuels like that. If you make small changes to the fuel, you make a big change in octane, which is the ignition delay. This is the same plot represented as a cycle. So here's the main path was around like this through the keto hydroperoxide, that guy right there. And then there's a bunch of these side channels, some of which get rid of HO2s and some of which make more OHs. All right. Now we wanted to know why the heck is stage 1A different than stage 1B? And what we figured out was that at the end of stage 1A, let's see what happens here. Well, during stage 1A, right at the beginning, we're having an exponential rise. It's like an explosion, but the total concentrations are so tiny that it doesn't really make the temperature rise much. So there's not enough going on. But if you look at the species, they're growing exponentially. So they're like what happens in an explosion. And so the OH is equal to some concentration times e to some lambda t, and this is like the explosion lifetime. And so I told you this rose five orders of magnitude. So this went through 10 1 over lambda times during that stage 1A. And all the other species are doing it too. So the keto hydroperoxide is rising exponentially. It's, here's one constant, here's a different constant. Same time constant for the rise. They're all rising together. And one of them is HO2 is being formed, and it's rising. But the coefficient for the HO2 is larger than most of the others. So the HO2 is growing pretty fast. And what can happen is that HO2 plus HO2 starts to be important. And this reaction makes HOOH plus O2. And so this is the main way we're making the HOOH. And what's happening is this exponential rise goes until this reaction becomes competitive with all the other reactions. And this starts sucking the HO2 away. So the HO2 concentration versus time, it was exploding. And then at some point it's going to start to die because here it's limited by the HO2 plus HO2. And I draw this in a small scale, but this is actually 7 orders of magnitude change from here to here. So it grew exponentially for a long time, but then it suddenly, it's saturated because it made so much HO2 that it starts to self-recombining. So early on, I have a lot of HO2, and the HO2 is contributing a lot to the consumption of the fuel. So at the short times, HO2 is attacking the fuel and making some radicals, and it's pretty significant compared to the OH reaction. So they're all the same order of magnitude. So the HO2 and the OH are both important for pulling away, destroying the fuel. Afterwards, when I'm up in the saturation region, the HO2 stopped climbing because it's self-limited. But the OH, if I make the same plot, here's the OH. It's a lower concentration to start with. It grows exponentially much the same, but then it keeps growing exponentially. And so the OH takes over and is the main radical. So in stage B, stage 1B, it's all OH, and the HO2 is hardly doing anything. Okay, so that's the difference between stage 1A and stage 1B. If you look back at the figure here, that during this region, we're rising so rapidly because both the OH and the HO2 are eating up the fuel, and they're both rising exponentially. During this region, the OH is still rising exponentially, but the HO2 is doing nothing. So it's not helping the reaction happen. All right, so you can analyze a system like that has a single exponential rise with eigenvalue analysis. And so we did it, and then you can actually predict sort of analytical formulas for what should happen. And so, for example, this is the simple eigenvalue analysis of the system for the OH rise. And we say during stage 1A, you get one slope on a semi-log plot. On the second stage, you get a pretty different one. Now you can see it doesn't exactly match the real solution, and that's because the real solution has all these nonlinear terms for all the side reactions and stuff. But ballpark, that's a sort of ballpark explanation of what's going on. What's really interesting is that the temperature rise really matters. So there's that little dinky temperature rise that you saw at the end of stage 1. Even before that, the temperature rises a tiny bit. Hard to measure experimentally, but you see it. If you look carefully, you have like 1 or 2 Kelvin rise. That actually is really important. So if you make a simulation where you force it to be exactly isothermal or no temperature rise, then the keto hydroperoxide lives a long time, and it hardly decays away. But if you make it adiabatic, so the temperature does rise, the temperature rise really kills the keto hydroperoxide because the keto hydroperoxide reaction has a very high EA. It's super sensitive to temperature. So even a couple degrees Kelvin rise in the temperature is enough to really increase its decomposition rate. Whereas the formation rate is not sensitive to temperature because it's all like OH reactions. The OH reactions have tiny little EAs, so basically they're T independent. So you increase the temperature, it doesn't make the formation any faster, but it really makes the destruction a lot faster. And that turns out enough to drive it down. And if you can mess around with the rate constants don't matter. It's all about the temperature is driving this. So basically, this is 2 different cases where we've messed with the rate constants and also to the temperature. And the temperature effect is much huger. So it's really all about the fact that the temperature rises a little bit. And even in systems you think are isothermal, if they're exploding systems, it's very hard to really make it completely isothermal throughout because the temperature wants to rise because it's going to explode. So then we applied those eigenvalue analysis formulas to a lot of other alkanes. And you can see that the low temperature, the stage 1 ignition delays are pretty well. So this one is propane. And then these are butane, pentane, heptane. And you can see that the simple eigenvalue analysis, it doesn't quite exactly match these tails, but more or less, you have the main story. So the main story is that at the low temperature case, that lambda, the rise time, the exponential, is slow enough that it's important, and it's most of the total ignition delay is just about that. So at low temperatures, it's like this, that most of your time you're just going along here to here. We can predict tau 1 pretty well by eigenvalue analysis, and this is close to the overall, so you're kind of close to the overall ignition delays. At higher temperatures, this is not going to work because the eigenvalue analysis is predicting stuff that gets way short compared to it. What's happening is that we're getting like this, where the tau 1 is now much shorter than the total ignition. And in fact, if you go to higher temperatures, it looks like this. So you see the little dip right over at the beginning, and then this goes for a really long time. And so then the tau 1 becomes less and less relevant for the real ignition problem at the higher temperatures. So we'll have to figure something else about the stage 2, which we haven't figured out yet. All right, so that's all I had to tell you about that. Questions?
Can you comment on the correlation between NTC region and double stage ignition? I mean, if there is NTC region, there is, then we can conclude that there is double stage or something like that.
That's a good question. Sorry, the question is, if I see NTC, let me see, I'll show you what NTC is. If I see NTC, which means that the ignition delay is not monotonic with the temperature, if I see that, can I conclude that I have two-stage ignition? That's the first question. And then there's the reverse. If I see there's two-stage ignition, do I know I have NTC? I think not. They're definitely related to each other, but I think there's cases where it looks like this, where the total ignition delay does never, it's always monotonic, it just, the slope changes a lot. Actually, a lot of fuels do this, even isooctane. If you do a plot of the ignition delay of isooctane, which is a very high octane fuel, it does this flattening thing. So when you look at plots of the log of the ignition delay versus like 1/T, almost all of them look the same out here. There's like straight lines, like Arrhenius. And they all look like Arrhenius in here. And usually these two lines don't match up because they're different processes. This one is mostly to do with H plus O2. And this one over here is something to do with the OQOOH. So the slopes of these two are different for sure. And not only the slope's different, they're not even continuous. And so then you have a possibility that it could connect like this, or it could connect like this, or anything in between. And some fuels do one and some fuels do the other, and sometimes it depends on the pressure and the temperature and the pressure. And I don't know. I don't know what it is. So the fuels that show this big swing, I think they almost always show two-stage. So maybe the first thing you said, NTC implies two-stage, is probably correct. But I think a lot of fuels that show kind of flat regions in here also still show two-stage. And then sometimes people don't report something as it being a two-stage, but I think it might just be to do with the error bar, the precision that they can measure the temperature. So to see the two-stage is kind of difficult because you have to see this little dink. And if you have your temperature measurements like this, with your noise, sometimes you might not see it. So I think right now, my tentative hypothesis is that everything does this little dink thing. It's just the magnitude of the dink could be different for different fuels, and so it might be too hard to see. But maybe I'm wrong. So all we've done so far is N-alkane, so I haven't tried to do. There's a lot of other fuels in the world. Other questions? Yes?
Could you go to that graph with the two bars, red and blue one? The other slide?
Yes? Sorry.
The other slide.
Oh, sure, yeah. Yep. Whoops, where am I? I'm on the wrong slide deck. Am I? Where is it? Oh, here we go. Yep.
So you have there the linear and the branch now can compare.
No, these are all for propane. This is just for propane. So propane is unusual because it makes more HO2 than most fuels. And the reason why, where should I do this? Over here. So propane, CH3, CH2, CH3. So when a radical attacks it, it has two possibilities. It can either make the N purple radical, or the iso. And this one, when it reacts with oxygen, this one almost 100% goes to HO2 plus propylene. This one, when it reacts with oxygen, primarily goes to the QOH cycle. So it makes like OOCCC dot, and then this goes to HOOCCC dot, and this adds another O2, and eventually this makes more radicals. The reason why this one does this is that the transition state for here to here, C, 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 H, O, O dot, this is six-membered ring, 1, 2, 3, 4, 5, 6. And so the barrier is lower. Six-membered rings are easier to form. They're not as strained geometries for the molecules. So this is a pretty low barrier to do this conversion from this to so this is actually pretty fast. But if you try to do the same thing for the isopropyl, you'd have to make a five-membered ring. And the five-membered ring is about 6 kcals per mole higher in energy because of the ring strain. And that turns out to be enough to make the other one. So if you do this, it makes, what it really does is it goes to C, C, O, O dot, C. And this has a choice. It can either go this way, or it could go to C, 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 O, O, H dot like that. But it turns out in this competition between these two, this one is lower because this one has a higher, is more strained. This one is a kind of strange one. It involves stretching. It's like a consorted reaction where this H stretches at the same time that this stretches, and at the same time this gets shorter. And that was discovered in 1996 by Schaefer's group. It was kind of, no one knew about this reaction until then.
So what is
Sorry, yes?
In one of the graphs where we show the difference between region A and region B, so it says that the OH, it shows the curve for OH, but you just said that OH is supposed to grow exponentially in stage A and as well as stage B.
Yes.
So,
Yes, good question. The question is, I said that this OH is growing exponentially in both stages. What the heck is happening? It looks like it's not, something's happened, right? Okay, so here, this is a semi-log plot. Any straight line on this plot is an exponential growth. So here, the OH is growing exponentially, and the time constant of the growth is something that's 1 over the slope in whatever the right units are. In here, it's also a straight line, more or less, from here to here, except the slope is way flatter. So the time constant is much longer. So why is that? Why did the time constant change? The OH is still doing the same thing it was doing before. And the reason the time constant changed is that the overall time constant has to do with the whole cycle. So back here, this whole cycle, the step from like the fuel to make RH here, when we always have the OH reacting with the fuel to make R, but in some of these cases, the HO2 we were making is also reacting with R and kind of feeding stuff back into the cycle. And that makes the cycle go faster. And the cycle is a little complicated that this, we have to make this thing explode, to have an exponential rise, we have to have more green than red. You have to make more radicals than you consume. And the two of them are actually very tightly balanced. They're almost the same. And so the small change in how much you push this along because you get some HO2s to come back in and push and make a few more greens, that turns out to be very significant for the overall time constant. So I don't know, it's like totally unclear. Yeah, question?
Now, first question is, in this stage 1A and B, does temperature explain the decay in the exponential growth? Temperature increase a little bit, does that?
The temperature increases a little bit. Yeah, maybe in a second order way. Yeah. So what's very important for the exponential growth is that we need to have the keto hydroperoxide. And the temperature is rising. Do you see it's slightly going up? Slightly going up. Do you see that? It's not very much, right? It's like 10 degrees Kelvin maybe from here to here, something like that. That's enough to make a huge difference in the keto hydroperoxide. So the keto hydroperoxide, the whole, when a thing is growing exponentially, everything is growing exponentially together. But then, first of all, the HO2 stops keeping up. Okay, now the HO2 was keeping up and he was pushing some fuel into the cycle. But now the HO2 is gone. He's went off to kill himself. All the HO2 guys are fighting each other. And they're not doing anything for us. And then the next thing happens is, because we're all pushing along so long, the whole thing gets a little hotter. We release a little bit of energy because of the oxidations that every time we go through this cycle, we release a little bit of energy, just slightly exothermic. So the whole thing's getting slightly hotter. And what happens to the heat is the keto hydroperoxide doesn't keep up. So the keto hydroperoxide, it was growing exponentially along with all the rest of them beautifully, and then it falls behind and reaches a maximum. And so it's not available to keep supplying the radicals at the rate that as much as it was before. And so that's sort of what's happening. But the kink happened back here between stage A and stage B. And I think that's before the keto hydroperoxide really did much, and also before the temperature did much. So I think that kink is almost 100% just to do the HO2, because it does correspond exactly to the point where the HO2 has its kink. So the first thing happens, so we have a system that's like a perfect linear system, and it has perfect eigenvalue analysis until it becomes a little bit nonlinear because the HO2 has recombination. But the HO2 reactions are not that important anyway, so it's just a small effect. It just changes the slope. Everything else keeps going like a linear system. Then it becomes a really nonlinear system once the keto hydroperoxide starts doing this, because this is like right in the main path, and it's no longer keeping up the exponential. And so the whole thing our whole model eigenvalue analysis isn't working anymore, and the whole thing poops out. And in fact, it goes almost completely gone. It goes away.
I read Haiwan's lecture about this, talk about the stability of R2.
Yep.
So
Yep. Okay, good question. Okay, let me pose a question. You want me to pose a question about that? Yeah. So I told you at the beginning that these are equilibrated reactions, but I haven't mentioned them at all, right? But they really are equilibrated reactions, even though I didn't talk about it. So all these guys are temperature dependent, all these equilibria, and the forward and reverse rates are very similar. They're like partially equilibrated reactions. They're all close to equilibrated. And so if you change the temperature, you change how those equilibria lie, it changes everything. And that's a huge part of what's happening in this phenomenon where this is going up. That means that the ignition delay is getting longer, even though the temperature is getting higher. It's totally bizarre. Why should it take longer to react at a higher temperature? And it's because those equilibria, some of them won't run. They just it's almost like they're blocked. They can't really run net because they're just running backwards faster. And so then all these side reactions start to take over because the RO2 can't get through. So it just falls apart. Maybe it goes back to R. Maybe it does these other side reactions. And so that the whole thing gets impeded by these equilibria that are not favorable. And the higher the temperature is, the more that's a problem.
I have a final question.
Yeah.
You mentioned about the chain length to the QH valve. Is there an optimum chain length that is most favorable?
Yeah, that's a great question. So the question is, if you have a fuel, is there some chain length of the fuel that really works well to make it ignite or not ignite? Because you might want either one. If you want high octane, you don't want it to ignite. If you want high cetane, you want it to ignite. And the answer is that so I said if you have a CCC dot versus CCC dot, this one reacts a lot better. This one, the crucial reaction that's happening is this, and this is a CH3 over there. It's pulling off one of these H's, right? So this is a 6-membered ring, so that's as good as you can get, because 6-membered rings are the fastest cyclization reactions. Always 6-membered rings the best. Okay, so that's the best. But this is a methyl group, which is a primary CH. Methyl groups have CH bond strengths about 2 kcals per mole stronger than CH2 groups. So if this instead had been a CH2 and maybe there was a methyl there, then this would be 2 kcals per mole lower, less endothermic, which means that the EA would be 2 kcals lower, so the whole rate would be faster by maybe order of magnitude. So this would actually be a lot faster. So butane is faster, and it's fastest if you abstract one of the methyl groups and then reach back and grab an interior CH. That's the fastest way. You can also have the other one where you have, for butane, you could pull off the H here and then make a peroxy here, and it could try to reach back, but now it has to grab the methyl, so this would be similar to the propane case. So once you get up, so propane is not that fast. Propane is bad because half the time you make these center C dots, which are useless. They make HO2s instead of OHs. And the other half of the time, you still have to extract a methyl with your 6-membered ring. That's not so good either. Butane is faster because half the time you're abstracting in the right direction to make it pretty fast. Otherwise, you're the same as propane. If you get to a long one, like heptane, one, two, three, four, five, six. In this case, almost all the time, you're going to extract one of these central CH2s because there's so many of these CHs that a radical comes up, most likely to hit one of them. So maybe you'll extract this one or something, I don't know. And then you make this OO dot. Now this can reach and grab from a CH2 that's 2 over, 6-membered ring, fast as it can be. So this is a very favorable case. If you started from this one, you still have a favorable case. If you started from this one, you have 2 favorable cases in 2 directions, so twice as fast. And if you started from either of the methyls, you'd have a favorable case. So no matter which CH you abstract from heptane, it always has a favorable case to make the reaction run, and it will make less HO2. So heptane has a much higher cetane number. It's much more unitable than some of the other fuels I showed you. On the other hand, if you're making gasoline, this is terrible because it means it's going to knock like crazy because it's always going to explode. So it depends what you want. But anyway, the long stretches of CH2s in a row, those are very, very good for cetane and for short ignition delays. And the more shorter segments you have broken up by something, then the more likely that the side channels start to compete because there's not easy channels for it to do the 6-membered ring reaction. And the exact details of that, exactly how they break it up and stuff, is still to be worked out. Yeah. Your questions?
Why is methane so hard to ignite?
Okay, so methane is hard to ignite. Several reasons. So first the CH4, the CH bond in methane is stronger than all the other hydrocarbons. So it's hard to get it to make methyl in the first place. But then you make some. And then the methyl, you think it could add O2 and go to CH3OO, similar to what we did here. But these molecules are so small that at normal pressures, this is usually in the low pressure limits. This isn't fall off. So this one is actually not as fast as you'd expect because it really needs a collision partner to make it go. Okay, so that means that this is actually pretty slow. So you don't make very much in this first place. And then what can this do? It can try to reach back. And it's only a 4-membered ring. 1, 2, 3, 4. So it's really strained. So it can do this, but the barrier is very high. So it's possible, but it has a really high EA. If you get to here, this will immediately fall apart, and you'll make an OH, and you'll make a CH2O. CH2O is actually really bad for ignition. Let's see if I can explain that. Because if you abstract, suppose you have OH plus CH2O, you make water plus HCO. But at low temperatures, HCO reacts with oxygen. It makes this thing, HCOO dot. This is a four-membered ring. Kind of weird, actually. But anyway, this one is similar to the isopropyl one. It doesn't do the abstraction reaction. Instead, what it does is this H kind of stretches out. This CO bond stretches out. So it can kind of reach over and it ends up as HO2 plus CO. So what this reaction did net was convert an OH into an HO2. The OH is very reactive and the HO2 is very unreactive. And also in these conditions, usually the HO2 recombines and just goes away, so it kills off radicals. So the whole process for methane, normally you'd start with OH plus CH4 to make your methyl. So you consumed an OH. You got one OH back, so you're net neutral. But then you consume another OH to react with the formaldehyde, and then you don't get it back. You get an HO2. So overall, you didn't make any radicals. In fact, you just converted an OH into an HO2, which usually slows things down. So methane is very hard to ignite. And in fact, the way it burns is actually through the second order reaction. It's totally bizarre. The CH3 plus CH3. That these guys recombine makes C2H5 plus H. This goes to C2H4 plus H. And this eventually goes to C2H3. And finally it burns. And you get CO. Or, well, HCO plus formaldehyde. But so you're going to make formaldehyde again, so it's going to kill some more OHs off. So this whole thing is just like not, it's hard to make methane burn. It doesn't want to ignite. So it's fighting you at every turn. All right, more questions? Okay, I'm done my slides. It's getting kind of late. I suggest maybe we take a break now. People want to chat with me some more. I'm happy to talk chemistry about this all day, but I don't know how many of you guys are really into it. So for those of you who are, come back after a break and we'll talk some more. And otherwise, I want to thank you guys. You're a really friendly audience. I appreciate it.